This is Chapter 1, Science and the Universe, a Brief Tour. This is the OpenStax textbook, which you would have downloaded online for free. This, by the way, is a famous picture taken from the Earth on one of the Apollo missions. It's called Earthrise. This picture was one of the first views of Earth as a planet from another point of view. This is late 1960s, early 1970s. Civilization first got to see Earth as a planet. And when we did that, that launched the modern environmentalist movement with this very iconic picture, one of the most published pictures of all time, Earthrise. You can also see a couple of other things. The planet is misnamed. It should be called Oceania. It is the water planet, not the land planet. You see the omnipresence of clouds. Clouds. The whole planet is enshrouded. And then you also see that exactly half of the Earth is illuminated at any one time. And of course, that says something about its orbit around the sun. In astronomy, we ask and give unique answers to the big questions. Who am I? Where are we? What is the shape of the universe? What is light? What is science? How did our solar system form? How did our planet form? Many, many basic questions about the world around us and the origin of our modern civilization go back to astronomy. Astronomy, you see lots and lots of pictures. Pictures are very interesting. They tell us a lot of information by interpreting the light. And there are many patterns and things like that. If you had taken a picture like you're seeing here in the early part of the 20th century, it would have just looked like a smudge, maybe a cloud. But there you see how astronomy progresses. Now the image gets clearer and clearer and clearer as technology gets better and better and better, until the smudge now turns into two galaxies that are merging together. A unique phenomenon. What's causing them to merge together? Whole suite of basic questions that science seeks to find answers to. What's happening here? This was taken by the Hubble, which caused a revolution in astronomy because of the clarity. It allowed us to see hundreds of times further back in time and space. Images that were fudges became images like this. We even have the successor to the Hubble called the James Webb Space Telescope, which was just launched last year and is 10 to 100 times better than Hubble. Here's a picture of Mars. Wonder who took this. Could be Hubble, but you see the Mars Marineris, the Valles Marineris, the largest valley in the solar system, registering as a giant scar across the face of Mars. How did that get there? Notice Mars does not appear to have any clouds. Doesn't have an atmosphere, in fact. Interesting. Why not? Too small. What you're seeing here is the remains of an exploded star. Supernova event that was seen by the Chinese as this big explosion in the year 1054. They recorded it. Perhaps the earliest known example of a supernova explosion that gave rise to something called the Crab Nebula. The Crab Nebula. This actually is where we came from. All of the material in our solar system was once part of an ancestral giant star that exploded and turned into a planetary nebula, which recondensed to form our solar system. Mind-boggling. Look at the different colors. In this class, you'll see a lot of pictures with different colors. How are those colors made and what do they mean? We'll talk about that, but this could be temperature, hot versus cold regions. It could be the type of light, ultraviolet versus infrared versus visible light. Could be that. Could be just in the infrared, because there are different regions of the infrared, the long infrared and the short infrared. So hopefully in this class, you'll gain some appreciation of what these color-coded images mean. And actually, I'll talk about how they are collected. And by the way, if you look up in the sky, try to locate a star called Betelgeuse. That star is predicted to go supernova any day now. Any day now. You could look up in the star and see a white flash, where now you just see a white dot. Supernova happening in our lifetime right now with Betelgeuse. It's going to turn into one of these. Here's another nebula called the Nebula of Orion. This is the far left star in the constellation of Orion. There's Orion's belt, which is 3 stars. Beneath the furthermost left one, goes south, and there you find what looks like a smudge in close up, revealed again by Hubble, is a giant nebula. What is the significance of this? Well, all these dots in there, that's where stars are born. This is a stellar nursery where stars are born. There's a close-up of this. If you want to look up an amazing picture called The Pillars of Creation. After Earthrise, The Pillars of Creation is one of the most famous pictures of all time. And I believe it's a close-up of that region right in there, if you can see my cursor in the upper left corner. So that's a nebula. Here's a picture of Hubble. I believe it is still transmitting data to this day. Here is a fascinating scheme presented by Hubble. And you're seeing the whole universe here. The prevailing theory about the origin of the universe is called the Big Bang, in which about 14 billion years ago, a primordial explosion happened that created all of the material in the universe. Well, what started the Big Bang? I don't know. What came before the Big? I don't know. I'm just telling you the prevailing theory. And as we go through the class, there are some very compelling pieces of evidence for the theory. Does it answer everything? No. Is it incomplete? Yes. It's the best we got, and it explains a heck of a lot about the universe we see around us. It matches measurements and observation. So until someone comes along with a better idea, we're sticking with this one. The primordial explosion 14 billion years ago. It's a very simple theory, really. It goes back to E equals mc squared, where E is energy and m is mass. When the Big Bang happened, all of the energy that was in the universe got converted into mass, according to E equals mc squared, and all of the matter in the universe was created in that trillionth of a second. If you start outwards from the Big Bang, we have the radiation era. That's when the only thing that is around is energy. There is no mass because it hadn't been transformed into the mass yet. It's cooling. As it cooled, we see here we're in the dark ages. So there's no light being emitted by anything because there's no matter yet. You just have particles smaller than electrons floating around, not emitting light, the dark ages. And then the electrons and the protons and the neutrons began to turn into all the atoms on the periodic table, and those began to coalesce, the first stars, the first galaxies, and so on and so on and so forth, all the way back to the far left where Hubble is looking now. Now look at the graph here. We're seeing Hubble deep field, which is this purple line, could see all the way back to 1 billion years after the Big Bang. So that's about 13 billion years ago. All the way back, Hubble deep field to within 1 billion years. You can see that's actually pretty close to the Big Bang, right? Then a scientist figured out a way to adjust mirrors and put filters on there. And Hubble ultra deep field could see back all the way back to 0.4 billion. That's 400 million years after the Big Bang. That is very quickly after the Big Bang, actually. All the way back to when the first galaxies were formed. A stunning piece of understanding about our universe. And this picture also reveals the relationship that time and distance are interrelated in astronomy. Time is distance and distance is time. It's like saying to your friend, I'll be there in 20 minutes. Well, you're going to get in your car and you're going to drive for 20 minutes and then you're going to be there. But that's also a distance, isn't it? Could be 10 miles. So we're actually very accustomed to interrelating time and distance. And that's a fundamental thing to understand about the universe around us, is that they are coupled together. So Hubble allowed us to see very quickly back, very further back. Now imagine James Webb Telescope. How far back is that going to see? Well, you can see from this graph that after a certain point, you ain't going to see nothing. because there's no light. So it would just appear as a black background. Not sure we're quite there yet. Something to follow in the news. How far to the Google, how far back to the Big Bang can we see? Can we ever see anything that's over here on the other side? Is there a boundary? No. The reason the answer is no is because the light would not have had time to reach us yet, and it never will. Here's our home base, Spaceship Earth, Oceania. Again, a very, wasn't this picture, it was that Earthrise picture earlier. This is a composite picture. They put a whole bunch of different images and connect them together to create a super clear image of our planet from a planetary point of view. So, astronomy has lots and lots of different aspects to it. We're in a revolution in astronomy, which means that there are big breakthroughs happening all the time. Here's a big breakthrough. We just discovered a new feature on Neptune. New feature on Neptune, never seen before. What is it? How did it get there? What causes it? Happening all the time in astronomy. We've learned from meteor collisions here on Earth that 65 million years ago, a giant asteroid whacked into the Earth, kicked up a big cloud of dust, and wiped out the dinosaurs. We can see that because the evidence of the cosmic collision is still present. We know where the impact site is in the Yucatan Peninsula. We've dated the sediment cores. This is how we learned about the extinction of the dinosaurs, which, of course, if that didn't happen, we wouldn't be here because we were little tiny gerbils 65 million years ago. Rodents. We only came out at night to eat the dino eggs. They ruled the Earth for 135 million years. But the little rodents could survive when the temperature went down because the dust that was kicked up blotted out the sun. Oh, reptiles can't make their own heat. They're toast, except for crocodiles and alligators and snakes. And the little tiny rodents turned into us. There's a moon is so weak that if you threw a ball up, it would just keep going into orbit. A collapsed star so dense that you would have to squeeze every human being on Earth into a single raindrop, and that would be the density of this star, a collapsed star. Exploding stars whose violent end, subtext reads supernova, could wipe out all life forms on a planet. Cannibal galaxy, where you see one galaxy gobbling up another. This, of course, will happen to our Milky Way galaxy. We are running into Andromeda. Our nearest galaxy is called Andromeda, and we are on a collision course with Andromeda. A radio echo that is a faint but unmistakable signal of the creation event for our universe. That sounds very poetic. What they are talking about is when the Big Bang happened, the afterglow of the Big Bang is omnipresent in the universe. It's everywhere. It's called the cosmic microwave background. This next to last bullet is an absolute revolution in astronomy, a new kind of wave, which was predicted by Einstein in 1915. discovered 100 years later after he predicted their existence. They're called gravity waves, and they are ripples in the fabric of space-time. It's not light. It's not light. It's a gravity wave where the fabric of space-time itself travels as a wave. Just discovered 10 years ago. Huh. Incredible applications for the field of astronomy. Black holes. We won't really talk about those in this class. That's for our 114 class. We just took a picture of a black hole. How can you take a picture of a black hole if it's black? Because the black hole emits a ring of particles that do glow. The ring you see in the picture of the black hole is what's being emitted from the black hole. So in astronomy, it's a fun class because we get to talk about the universe. Well, there's a couple things about that. There's the observable universe and the total size of the universe, the actual, how big it is and what is its shape. We do not know the total size of the universe or the overall shape of is the universe finite or infinite? We don't know. Is there a multiverse? We don't know. The only thing that I ever have to say in this class is about the observable universe. What is actually seen? Total universe is very mysterious. Here you can see from Earth our Milky Way galaxy. What? This, what you're seeing, that glow in there, is the glow of the central halo of the center of our galaxy. Inside of which, within which, we just discovered a few years ago that there's a black hole. It is now hypothesized, not proven to be true, that there is a black hole at the center of most galaxies, and that black holes are actually key to understanding galactic formation. A few years ago, it was thought that black holes were very rare. Now they're quite common. For a long time, we couldn't see the Milky Way galaxy. We could just look at it much like this person. And the reason we couldn't see is because of this curtain, the dark junk, the cosmic dust and gas that blocks our view of where we are on the Milky Way galaxy. And this is one of the remarkable things about astronomy, is that using the right wavelength of light, it's actually the short infrared light, about 100 centimeters in wavelength, passes right through the dust because the wavelength is smaller than the particle diameter. So we can actually see right through the dust and can image all the way across the Milky Way galaxy. Now, this thing says, this image registers another very important point, which is where we are. We are not above the Milky Way looking down on it. That would give us a wonderful view of the whole thing. No. We are in the plane of the galaxy. You're seeing the galactic plane. Wow. So we are not positioned to have a good view of the galaxy, and that's why it took a long time for us to understand it. Excuse me. So here's what we did. We took our best technology and took pictures in every single direction. That's why you're seeing a spherical image. This is not really the shape of the universe. Excuse me. But here we are at the center. You can see we're not really at the center. It's just our point of view, our starting point. And you can look out and see the galaxy, the universe, the total observable, here it is, the total observable universe taken from every direction here on Earth. Here we are at the center, and what is that, about a centimeter or so is 1 billion light years. So that's several billion light years in every direction. This is what the universe looks like. It's called the cosmic web. Some people think it looks like a giant brain. And this is all the connective tissue in there. The image is kind of, it is exaggerated because most of the universe is actually empty space. Nothing out there. And so we're just condensing all the things that emit light so that we can get the overall picture of what it looks like. The distribution of matter is governed by gravity, the great sculptor of the universe that creates regions in space where there's a lot of matter that's attracting other matter around it, but mostly empty space. Notice that there are no patterns here. This is not intelligent design that we're seeing here. No godlike being did this. There's no shapes, no triangles, no angels, no wings, nothing. It's the random distribution of matter governed by the laws of gravity. So, each dot in here could be millions of galaxies. That's kind of a funny thing to think about. So here we are. You can see we're in the middle of the Virgo supercluster, which is thousands of galaxies in the Virgo supercluster. You can see a neighboring supercluster, the Shapley, that's our nearest neighbor, and then another one, the Horologium supercluster. Again, these are just clusters of thousands of galaxies. So how many stars are in the observable universe? This is a famous calculation. There are about 100 billion galaxies. So as you look in the observable universe, there's about 100 billion galaxies. That's written in exponential notation. 100 billion is 10 to the 11th. 10 to the 11th. In each galaxy, there's 100 billion stars. So in our Milky Way galaxy, there's about 100 billion stars. So if you multiply 10 to the 11th times 10 to the 11th, you get 10 to the 22nd. That is about the same number, 10 to the 22nd. That's a 10 with 22 zeros after it. That's about the same number as all the grains of sand on all the beaches of planet Earth, is how big 10 to the 22nd is. Each one of those grains of sand is a star in the observable universe. Well, that's quite a lot of stars, I would say. And it's actually a very good argument for why there are aliens. because there are so many stars. That's why. One of them has to have life, at least one, and it's probably millions of them. Here's just a notion about what the universe looks like. Could it be a multiverse? Could it be a multiverse in which each one of these, like scuba diving bubbles, each one of these is a separate universe? I can't answer that. I don't know if the multiverse is real or not, but it is getting some attention in the news. It hasn't been ruled out, let's put it that way. Scales in the universe are extraordinary. I just told you that there are 10 to the 22nd stars in the observer. That's just a very, 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 very big number. Sizes of objects, too, is almost incomprehensibly big. So here you're seeing an image from your textbook. By the way, that when the figures are listed here, this is a prompt for you to go and read about it. If you want some more details about any of these topics. So this picture is drawn to scale. So you're seeing basically the only show in town from our solar system point of view is the sun. In fact, 99.99%, and that is 0.99, could be 0.999, of the mass of the entire solar system is in the sun. Less than 1/100th of a percent is the mass of the planets in the solar system. You can see how tiny Earth is. It's large compared to the terrestrial planets, but very, very tiny compared to the gas giants, Jupiter and Saturn. Here you're seeing, oh, look at that, a dwarf, there's Ceres. Look at a dwarf planet. Look at that. Sitting in between Mars and Jupiter, not shown in this picture, is the main asteroid belt, in the center of which, the biggest object in which, is a dwarf planet called Ceres. You're seeing other dwarf planets out here. All you can see why they're called dwarf planets. This is another asteroid belt, the outer asteroid belt after Neptune. These are called trans-Neptunian objects, TNOs. But all drawn to scale. I could keep going here. I didn't put this on this slideshow, but if you look at the sun as a star, you think the sun is really big. It's actually a small to medium-sized star compared to Arcturus or Betelgeuse, which are thousands of times bigger than our sun. So there are many different scales of size in the universe and vast differences between the sizes of objects. Here's one where you see the Earth and the Moon. The Earth's moon, I mean, let's give the moon some credit here. Earth has the largest moon relative to the size of the planet of any of the planets in our solar system. Earth's moon is about 1/3 the size of Earth. And that's pretty big. That's pretty big. So that was a brief tour. Let's move on to the next topic in this chapter, which is called the scientific method and is all about the nature of science. So section 1.2, the nature of science. Science comes from the Latin word scere, which just means to know. So part of science is just accumulating knowledge. And then, of course, we want to take the knowledge and order it into patterns. These are called natural laws, and theories. Theories explain the laws. So everything in this textbook, all the results and conclusions fit into the scientific method. And it's also, I think, important for being a citizen of Earth today. We have many different phenomena that are happening in the world around us, like global warming, for example. But there are others. And it's important to be a scientist when analyzing the data and making your own conclusions and using scientific reasoning that's based on facts to understand and come to a conclusion about what your view on a certain issue is. You know, a similar thing happened hundreds of years ago when most of the world believed that the Earth was at the center of the solar system and the universe. Everything was revolving around Earth. And then a scientific revolution happened. And that revolution changed our way of thinking that was based on fact that the sun is at the center of the solar system and there is no center of the universe. That's called a scientific revolution. When most of the people think one thing is true about how the world works, and then evidence is brought forth, ideas are tested, and a new reality is confirmed, a new understanding is reached. And that's happening all the time, and you can apply this to many different pursuits in your life. And so let's take a few slides to learn about the nature of science and the scientific method. It's important to understand that the ancient peoples did not practice modern day science. To give you an example, what the Greeks did, although the word skade does ultimately go back to Greek, the Greeks did invent science in some kind of way. There's no doubt about that. But they were missing a key aspect of it. So what the Greeks did was stuff like, hey, let's go into a cave, build a fire, cook some pig on a spit, and let's talk about the universe. I think God created the universe, and if God is a perfect being, everything in the universe must be a perfect shape. And the perfect shape to the Greeks was the circle or a sphere. Everything travels in a circular orbit, perfectly circular orbit, because God is a perfect being. And the other guy says, this would be Socrates, yes, by Jove, I think you're right. And that became the paradigm for thousands of years. What were the ancient Greeks and Romans missing? You got to test it. You got to find evidence. Evidence. They didn't think to go out and, well, they actually did, but they didn't satisfactorily go out and use facts to support their theories. They came up with theories before there were any facts to support them. That's not science. So I hope as a result of taking this course, and you'll learn something about how science is important to a lot of different areas. So you can think of the scientific method, that's what's being shown in this slide, as gears. And this gear turns this gear, which turns another gear, and so forth. It's the machinery. You see actually the gears here, the gear wheels turning. Science churns. It churns data, the collection of facts, into patterns and theories and knowledge. That's what it does. And the first thing, I would take a step back and say what science is trying to do is a very natural thing, because what it's ultimately trying to do is take information from the senses about reality. You have 5 senses: sound, smell, taste, touch, so forth, sight. These give us information about the universe around us. And not just the senses, but now we have technology, which is an extension of those senses, microscopes and telescopes and so forth. And this is giving us a vast amount of information about reality, the world around us. So the purpose of science is to organize phenomena, information that's coming from our senses and the extension of the senses, and organize all of this information into patterns and laws and theories and knowledge. So you start with an observation. This is the information coming into the senses. Oh, you're on a whale cruise. You see a whale breaching. You see, an observation is, again, a vast variety of phenomena. Look at the ribbon of energy behind me. That's a pretty good observation. And now you have to understand it. So you suggest a hypothesis. That's a key step in the method of science. A hypothesis is a tentative explanation for the observation. Tentative explanation. So, for example, the whale breached because it's like a peacock and it's looking for a mate. The ribbons of energy that you see behind me are produced by molecules that are getting excited and produce light. Okay, that's a hypothesis. The key thing about the hypothesis is it has to be testable. If you can't think of a test for the hypothesis, then the hypothesis is useless. Useless. Throw it out. The reason the whale breached is because someone from the planet Nebulon in a far-off galaxy was sending subconscious subliminal messages to the whale telling it to breach. Might be able to test that. I can't think of an obvious way to do it. If it's not testable, it's useless. And that's part of the creativity in science, is coming up with a clever experiment to test the hypothesis. Here's one for you. The Earth is actually spinning so fast you can't even see it. Huh. You look out the window. No, it's not spinning at all. How could you test the hypothesis that the Earth is spinning? In the middle of the 19th century, somebody figured out a way to do just that by creating a gigantic, can you fill in the blank here? Pendulum, a gigantic pendulum called a Foucault pendulum that you can see in a good science museum. Knocks over the dominoes. That's the experiment that showed that the Earth is in fact rotating. And the reason we can't see it is because we're inside the frame of reference of the Earth. If we were outside the frame of reference of the Earth, coming towards the Earth, we would see the Earth spinning 1,000 miles an hour. So the hypothesis explains the phenomenon. You have to test it. Testing really means making a prediction. This is why science is a prophecy. It does predict the future in a very basic kind of way. So the prediction would be that if the whale's breaching, if it's looking for a mate, the prediction would be then you would see a bunch of female whales around. That's the prediction. You can test that. Do a survey. Are there a lot of female whales around when the whale breaches? Is it a male whale that's breaching? And so forth. Make a prediction. I could tell you one about the ribbons of light behind me. There are many. There are other ways. If the earth is spinning, then what? That sort of thing. Okay, you do the test. You see the gear turns. You do the test. Do the results support the hypothesis? Well, if that's a yes, hey, that's a good thing. And now we're over here to this gear on the far right. If the test provides evidence to support the hypothesis, make additional predictions and test them. Okay. So you don't just do one hypothesis and one test. One test of a hypothesis does not mean the hypothesis is true. You've got to test the hypothesis 6 ways from Sunday. When many different predictions of a hypothesis turn out to be correct, well, what's not shown on here is the next step in the scientific method is a natural law. You have a pattern of nature. If many different tests of the same hypothesis, the earth is spinning, that's now a fact. No one really disputes it because it's been tested 6 ways from Sunday. So this whole process of the gears turning leads to, not shown on this diagram, laws and theories. Okay, now here's part of the beauty of the scientific method. What if it fails? There's no other whales around when the whale breaches, and so forth. Do we throw up our hands and say, well, we can't explain this one, let's move on to the next thing? No. What you do, and is there an arrow missing? It says make more observations, revise hypotheses, or choose a new one. So what's missing on this diagram is they should have an arrow going from this red circle all the way back to both of these. It's circular. It feeds back upon itself. It goes back. Come up with another explanation. The whale's breaching because it's scratching parasites off its back, and so forth. And you make a prediction about that. And there you see how the gears of the scientific method churn. It's self-correct. The whole system is self-correcting, because if the hypothesis fails the test, you create a new, build a better mousetrap, improve your ideas, make better measurements. So these steps can be repeated indefinitely until, again, you churn out laws and theories. Notice also this third bullet here, all scientific knowledge is provisional. It's provisional upon the test of the hypothesis. So a hypothesis could succeed some tests, but fail in others, and so you need to revise the hypothesis, make corrections to the hypothesis. It's provisional. It's ever-changing. Ever-changing. So science is constantly evolving. Wonderful, wonderful. Notice here, and just one last point about this is this dangerous word called the truth. People that don't understand science think that scientists are all about the truth. This is the answer. This is the why. They believe in the existence of absolute truth, as say it's written in a religious text. Something that's written in a religious text, if you believe in the absolute truth of the text, you believe that's the direct word of a higher power. No. That's not how science does not believe in any absolute truth at all. All scientists are non-absolutists because we understand that there are degrees of truth and that you never reach the actual truth because someone can always come along and build a better mousetrap, collect more information, come up with a better hypothesis. Theories can be revised. A perfect example is the theory of gravity by Isaac Newton, held sway for 250 years until Albert Einstein came along and said, well, it's not quite really correct now, is it? No such thing as the absolute truth in science, only degrees of truth. So here you see the further bigger picture here. Here you see the circular nature, but again, the endpoints are laws, contributes to knowledge, and theories. So theories are large umbrellas of hypotheses. Many, many different hypotheses feed into a theory. The theory is the why. The pattern becomes the law. So make sure you appreciate the difference between a theory versus a law. And you can think of the theory as the why. For example, the theory of evolution explains the why we evolve, survival of the fittest, blah, blah, blah. Atomic theory, which has the assumption, all theories have postulates or assumptions that if this is true, and the great assumption of atomic theory is that atoms exist. And once you recognize that as being true, then you can explain the behavior of matter using atomic theory. So theories explain the why, and the law is a pattern or rule of nature. The law of attraction. Electrons and protons will be attracted to each other. That's always true. It's a general, there's no why there. It's just the pattern. In chemistry, you have the gas laws. As the pressure goes up, the volume goes down. That's a pattern of nature, and so forth. So again, just make sure you can appreciate the difference between theories versus laws. There are also things called scientific principles. And there's two of them in this class, Occam's razor and the cosmological principle. Occam's razor will come into play, and you'll see many examples of this in your life if you actually think about it, that if you have competing hypotheses, competing explanations for the same observation, Occam's razor says the simplest one is correct. The one that has the fewest assumptions and postulates and isn't so needlessly complicated. Occam's razor says that nature's laws are simple and they don't require complicated explanations. So that's Occam's razor. And we'll see how that comes into play during the Copernican revolution that we discuss in this class, where there were competing hypotheses. And it turns out that to explain something called retrograde motion, it's much simpler to assume that the sun is at the center and not the earth. So we'll come across Occam's razor in chapters 2 or 3. The second principle is called the cosmological principle. And this really is important in all things because it basically says it permits us to understand the universe. It says that the force of gravity, the way the apple falls from the tree on Earth, is the exact same way an object falls from height on some distant star. In any place in the gravity works the same everywhere. The physical laws that work on Earth apply also to the universe. Electrons and protons in another galaxy will still obey the law of attraction. That's the cosmological principle. And it's so important because if it wasn't true, then we couldn't understand what is out there. Cosmological principle allows us to assume that by understanding things in our backyard, we can extend our understanding to the larger observable universe. 2 principles. Astronomy is an observational science. This as opposed to chemistry. Chemistry would be an experimental science. You mix the two things together in the beaker, you heat the beaker, you produce something, you measure the experiment. Astronomy is much more often, hey, look, let's take a picture. The picture is a snapshot of the observation. Very good for photography. Astrophotography is an incredible field. Observational science uses models. Models, in a scientific sense, are math. The math is the model. Yes, the math can also be the law, which is why math is the language of science, because you can understand the model using equations. And there's also physical models. Think of, for example, the Ptolemaic model, which we'll get to, is where you have the Earth at the center. It's an actual model. Earth is at the center, and then boom, 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 going outward. And these are used to make predictions and to make new observations, actually. So the very famous example of observational science and physical and mathematical models coming together is Albert Einstein. Not sure how much of him we'll get to in this class, but the greatest theory ever conceived by any human being is called the general theory of relativity. When he first came out with this theory, everyone thought he was nuts, except a few people. He was 20 years ahead of his time. But the theory made a prediction that could only be verified during a solar eclipse. There was a solar eclipse, and this famous astronomer named Arthur Eddington took his telescope and looked at the planet Mercury, which could only be visible during the eclipse because it's so close to the sun. So you need the eclipse to see it. The general theory of relativity predicted that the path of Mercury should change by a little bit, a tiny bit, as it came close to the sun. And he predicted the exact amount it should be deflected because of the curvature of the fabric of space-time around the sun. The prediction was exactly correct and was measured, that's when he became Albert Einstein. The scientific method is a method of testing the truthfulness of ideas, not a way of coming up with the ideas. This is why Albert Einstein said imagination is more important than reason. He was absolutely right. We must be able to think of new ideas and new solutions to new and old problems. God, do we need that? Unlike art and music, science theories are judged by nature. By nature. Has to be found and explain something in the world around us. Otherwise, it's what's the point? This is different than art and music, which just want to create beauty and aesthetic feelings. Not subjective to human juries. It's one of the things I love about it. It's the world outside of human beings. Not that I'm antisocial or anything. I talked about how science self-corrects. If the test fails, you go back to come up with new hypotheses and make more measurements. Goes right back to the scientific method. Old ideas can be falsified and rejected based upon new evidence. Theories are continuously revised. New ideas must be supported by evidence. If there is no evidence to support the hypothesis gets thrown in the garbage can. So here at the end, it gives the example of the Ptolemaic. This is the Earth-centered model. And then that was replaced. This is part of the Copernican revolution, which I will get to. There can be major overhauls and revolutions to scientific theories. And I gave the example of Einstein revising the Newton thought it was a force. Everything was a force. He called it action at a distance. Gravity is not a force at all, people. Not a force. It's just a ripple in the fabric of space-time. We are continuously gathering facts, and hallelujah to that. Here are some, patterns. You look at a tree and the 4 seasons, winter, spring, summer, and fall. And you look up in the sky and you see different constellations present during the seasons. There's a pattern there that every winter you see Gemini and toward the center, but it isn't there in the other seasons in the same spot. That's the pattern, how the constellations change with the seasons. So we see these patterns all the time, and that's what we try. Of course, we understand this now. And this, by the way, is something that Harvard graduates did not understand, is what causes the change of seasons. Most of the Harvard graduates thought that it was the changing distance from the Earth to the sun that caused the seasons. So when Earth is farther away from the sun, it's colder. Winter, dude. No. That's totally wrong. And as a result of taking this class, you can understand what many Harvard graduates, more than 50%, got wrong on their graduating exam of an education they paid 6 figures for. Go figure. Here's another set. Look at this. What you're seeing here is 2 black holes orbiting each other. Fortunately, we don't really talk about this in this class because it's beyond the solar system. We do talk about it in 114. Here's 2 black holes orbiting each other. A couple of neutron stars, those are the orange ones, orbiting each other. And they're producing ripples in the fabric of space. God, I love saying that. Gravity waves. just discovered in 2015, folks. Gravity waves, predicted by Einstein. And these waves are rippling through the Earth. And we can actually build an instrument on Earth. It's called LIGO, L-I-G-O, uses lasers. The entire Earth is rippling like an accordion. Very, 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 very tiny. Less than the diameter of a hydrogen atom, in fact. But we can measure that tiny, tiny ripple in the fabric of space-time caused when two black holes or two neutron stars orbit each other, and they create these complex patterns of gravity waves. Now, from the distribution of these waves, you can begin to understand what is going on in these different situations. Fascinating pattern to try to unravel and try to come up with theories and laws about how these patterns propagate through space. So here we conclude. I mentioned the Big Bang 14 billion years ago. Look, that's a long time, people. It's a very long time. It's too big for our, but we understand it with the budgets and billionaires and things like that. But in terms of actual amount of time, it's a vast amount of time. And that's the importance and the usefulness of the cosmic calendar, to try to get you to picture the vastness of time. How big actually is 14 billion years? And so it is here compressed into the cosmic calendar, where the entire 14 billion years is compressed into a single calendar year. So on January 1st, on New Year's, the Big Bang happens. January 1st, year zero. You see that the Milky Way galaxy does not form until May. January, February, March, April, May. So that's 4 months it took the first galaxy. Well, the first galaxies were a bit earlier in April. Milky Way forms in May. Our solar system forms in September. In September. October, God, we're getting late already. Earth atmosphere gets oxygen. Complex life begins in November. On December 19th, the vertebrates appear. On December 20th, something could finally pop its head out of the water because the Earth developed an ozone layer, and land plants appear on December 20th. The dinosaurs appear on December 25th. Mammals appear on December 26th. The dinos became extinct on December 30th. And on December 31st, it's actually just a few seconds before midnight, human beings appear. So in the cosmic calendar, compressed the entire history since the Big Bang, human beings would only appear at a few seconds before midnight on December 31st. We just got here. So that's it for chapter 1. Please contact me if you have any questions.